So as you see from the graph in the middle here, we wanted to develop a planetary nervous system that is connected to a living Earth simulator and also connected to a global participatory platform. And under the hood, there is an exploratory for economics, for technology, and for other things. The exploratory for economics is a little bit in the line what Dawn Farmer was telling us in the talk before. As I said, this project was very ambitious. The proposal unfortunately failed, as we know, but the question why is still controversially debated. Some would argue that with our digital twins that we were envisioning, we were ahead of time, as Alessandro Vespignani, for example, mentioned. Others were in favor of conspiracy theories and even political interventions that made the project not happen. I would argue that there might be other reasons, maybe that our reviewers did not really understand the goals of the project. Maybe we failed to describe these goals in a conceivable manner. In management science, there are different approaches to set up goals such that others understand what we are aiming at. And SMART is just one of the possible acronyms. And I ask myself whether in our common history, we had a time where we were following these SMART goals in our research. And I would like to explore this a little bit. Yeah. So I start not with the S of SMART, I start with the T, timely. As I said, in 1992, we worked together for the Sonderforschungsbereich 230. It's a collaborative research department that encompasses different institutions at different universities, in our case, Stuttgart, Tübingen, and Berlin. This research department was founded in 1984. That's the same year when the Santa Fe Institute was founded. And it was aiming at similar problems, namely to understand how complexity emerges in living systems. What was interesting for us that we had a collaboration of architects, of biologists, of physicists, of philosophers, and engineers. And in particular, Dirk and I were working in the project part E1 and E2, dealing with the principles of structure formation. So our task was to understand the self-organization of urban structures. So what were these architects and town planners interested in that they were consulting physicists like us? They were interested in the question whether these structures that they observe had some common underlying principles of generation and maybe even some universality. The founder of this research department was Frei Otto. You may not know his name. So let's quote Walter Gropius, that's the founder of the Bauhaus. He said about Frei Otto that he was among the most influential architects of the 20th century. And he said precisely, Frei Otto was one of a kind. So what was special about this architect? He tried to construct buildings from these free-forming surfaces that you see in the top right. This picture is taken from the Olympic Park in Munich, which is still existing here. But Fray Otto did not only construct these fancy buildings, he was also interested in how these structures emerge. And in the in the bottom right picture, you see a hand drawing by Fray Otto. He discovered a trail system of mice near the cottage that he owned in Warmbronn. So there's even the scale, if you can see it, 1 meter. So he was hand drawing how the trail system of these mice look like, and asked himself, okay, what's the commonality between these self-organizing, free-forming surfaces and trail systems like this? The other important figure was Klaus Humpert, a town planner, who was fascinated by these aerial photographs by the Swiss photographer Georg Gerster. You have to think 35 years back. And now we go on Google Earth and see all these things. At that time, this was not available. So Georg Gerster was a pioneer in this area of photography. Yeah, he was going with his plane around the world and just photographing structures. What you see here is the area view of a village in Mali. And Klaus Humpert asked himself, okay, well, this is definitely not a planned structure. How did the people in the village organize themselves in space? But he also thought about larger scales. So you see on the bottom line, the city of Berlin in 1875 and in 1945, and you see only the built-up area. Today, we have satellite images for this. At that time, people drew this from historical maps by hand. These were very unique and expensive pictures that we got. And the question that they asked, Klaus Humpert and Fray Otto, is how do these structures evolve if no one, like a town planner, is involved in structuring the surface? So that means the question of self-organization in urban structure was a very, very timely question 35 years ago. So what did we had to do specifically? Our task was to understand not just the self-organization or the co-evolution of urban structures. You see, there are two complementary structures that are built by two different activities. There are the settlements, that means we occupy space, and there is transportation, that means we access space. And the question is, how are these two different activities connected? So our task was to develop models of self-organizations that couple these transportation systems and the urban aggregation. And the idea we came up with was to understand this via a kind of adaptive landscape that you see here in the lower part of the figure. So there is a kind of potential or adaptive landscape characterizing the trail system, and another one that characterizes the built-up area. So you can think of them as spatio-temporal fields that interact with each other and evolve or co-evolve over time. And we wanted to see whether this can generate the urban structures. So the M from measurable means that we have to show some quantitative results. And these results regard the dynamics of these urban structures. If we look at to the left-hand side, then you see in the lower part, the city of Berlin, the black dots, the built-up area of 1910. And the red dots are the growth zones that, according to our model, have been occupied between 1910 and 1920. And on the top part, you see the respective adaptive landscape or the spatial temporal field that basically coordinates these spatial activities. So precisely what you see is the lower part of Berlin next to Potsdam. That's what's captured in the tracking field. On the right-hand side, you see examples of the trail system. The picture we know very well, it was already shown here. That's a view of Dirk, from Dirk's office. And what you see are trails on the campus, and you also see the shortcuts that pedestrians made on this grass area here. And the question was, can we understand how pedestrians optimize their movement by creating these new trails? And we also published a paper already in 1997 in Physical Review E, where we explain the dynamic principles of this type of trail formation. The A for achievable points us to the question what we would accept as an achievement. And this essentially means what we see as science. Is science there to generate a tool or a prediction machine or a living Earth simulator? Or should we first think about what is the overarching question that we want to answer? Astronomy is not about telescopes. And the second question about science is the ultimate aim to collect data and then use large language models to make sense of these data? I followed with interest the discussion about citizen science here during the workshop, and I think that this discussion neglects that data per se has no meaning. Science is the instance that gives a meaning to the observations. Do models quantify as achievements? If you think of the talk by Alex Vespiani, then it became clear to us that models are approximations, and we should not expect that a single model alone gives us all the answers that we are interested in. The models of urban growth and of trail formations that we created during our time, these were so-called generative agent-based models. Today, agent-based modeling is a very common perspective, but in 1995, 30 years ago, this was not at all the case. So we were quite advanced with our approach there. But generative ABM means that we are not aiming at forecasting, but we're aiming at understanding. We aim at identifying mechanisms and common principles. And this is indeed an achievement. I quote George Box here, the ability to devise simple but evocative models is the signature of the great scientist. So over-elaboration and over-parameterization is often the mark of mediocrity. But I would like to interpret the A little bit differently, from achievable to applicable. Because I think that this is the point where Dirk has made some of his most important contributions to science. The early pedestrian models that we were talking about have been over time developed into a full framework to explore evacuation scenarios. And this means that to these models, there was a completely new layer added that aims at understanding optimization. Optimization is an additional feedback that means we simulate, we quantify, and then we change the boundary condition in such a way that we achieve better or more wanted results. The largest application of this evacuation framework is probably the hatch, where Dirk was involved in optimizing the facilities for millions of people. And you see in the lower part of the figure that Dirk even consulted the Saudi government in how to structure these facilities. I would argue that this is a remarkable step to move science to the relevant and applicable level. On the right-hand side, you see that Dirk has used these insights from the evacuation management, from the evacuation simulations to develop a whole framework for disaster management. The picture that you see here points to a specific disaster, namely the disaster happening at the Love Parade in Duisburg in 2010, where there were 21 people dying. And the question that was also brought up to court is, who is guilty? Who can we hold responsible for this disaster? And the picture that you see here shows you not just the feedback, it also shows you the decision processes that basically feed into this feedback cycle. You see the red feedback cycle there, that's a vicious cycle. What's a vicious cycle? A vicious cycle amplifies whatever you put in as a direction. So it can make things much worse if you give it into this direction, but it can also make things much better if you are able to go into the other direction. So, and this decision diagram that are in these small boxes here, they tell us why this existing vicious cycle went into the wrong direction. So I think that this is a remarkable achievement to help people to also understand what the limits of their design and their construction is. So coming to the R for realistic, what we accept as realistic depends again on what we accept as scientific contributions, whether we think that models or theories are really a realistic achievement. Paul Samuelson said, every theory, whether in the physical or biological or social sciences, distorts reality in that it oversimplifies. But if it's good theory, what is omitted is outweighed by the beam of light and understanding thrown over the diverse facts. Yeah, that's precisely what we were aiming at, a beam of light and understanding thrown over the diverse facts. This is what we thought models should be. But this is, of course, only the first step. We could see our modeling as just a sequence of successive refinement. And the first refinement of the early models of pedestrian dynamics and urban growth, they regarded the representation of space. Space is not homogeneous as we were assuming on small scale. Space, of course, depends on topology, but there is even more. Space is adaptive. It adapts to our own activity. This is similar to relativity theory where mass curves space. On the left-hand side, you see the space, the two-dimensional space, as seen from the perspective of a population of mice. And this is an adaptive landscape. The way the mice behave in the space, the way they build their nests and so forth, so shapes this type of flat and homogeneous two-dimensional space. So that means the space is actually transformed by our activities. And in our effort to make models more realistic, we were, of course, studying what kind of space transformers we need to consider in order to get to more realistic representations. On this slide, you see two examples of how space is transformed by means of activity. On the left-hand side, you see the impact of economic activities that amplify the formation of spatial clusters. And this is a positive feedback that means it can, in the end, destabilize the system. It can increase the risk for whole areas to collapse if there are economic crises, for example. On the right-hand side, you see another space transformer. That's a paper from Dirk that I like very much. So, where he introduces the an effective distance to replace the simple geographic or two-dimensional distance. In this paper, you see the air transportation system on the top. So these are all flight connections. You see on the lower part two diagrams. The first diagram is mapped on geographical space. You see different cities very much distorted, so their place in this diagram depends on how they can be reached. And then you see the smart idea of introducing, instead of geographical distance, an effective distance, which the paper defines. Then you see miraculously that all these distances collapse into one scaling law. So I would claim if you have this picture, then you understand the role of space in certain dissemination or transportation phenomena. We can move the term realistic up to the other level, namely calling it rewarding. That means we take science to the next scientific level. And I think that Dirk's research is a very good example of this. Remember, these trail formation models, they were basically describing the dynamics of networks. Interacting agents form a transportation structure. And then the next level is how these structures are utilized. It means from the dynamics of the network, I move to the dynamics on the network. And this is what Dirk did in very remarkable research papers, namely to study the different patterns of traffic that can emerge on highways and in cities and so forth. I took a picture here from the last paper that was published where you see some optimization schedules that also try to use artificial intelligence. On the right-hand side, you see another possibility to utilize this dynamics of networks into a dynamics on networks. This is from our own work. You see a transportation network, and this transportation network describes the distribution of pharmaceuticals, and the blue path that you see are trajectories of how these pharmaceuticals are distributed in the US in real space. The red parts would also satisfy the needs of a customer, but they are not taken because customers have certain preferences regarding their suppliers. If we are able to manage to relax these preferences just a tiny bit, we have access to this red path. So if there is a shortage of pharmaceuticals, for example, we can utilize the red path, means change the distribution in order to have more time to overcome this shortage. Thank you very much.